Alright, so we got limiting reagents. So this is going to be the part 1 video. Because these problems tend to be a little bit longer. So it's easier for me to upload 2 separate videos because they won't take as long to upload. So we're going to do one problem on this video with mass, and then the next one, similar format, but it's going to be with a gas. And we need to find what volume. So we're going to use that 1 mole equals at standard pressure 22.4 liter units to area ratio in the next video. But let's start with this one first. So right here you're given an equation, and I kind of set it up here already, you have it on the worksheet. You've got aluminum solid, which is somewhat active, group 13, wants to lose 3. You've got diatomic oxygen, right, which we know is a nonpolar substance with smaller IMFs, right? Electronegativity difference here, that's why it's found at gas at room temperature. Well, when we react these 2 substances, what we wind up with is aluminum oxide in a solid form. So in a beaker, in the lab, they're giving us 5 grams of aluminum solid metal and 5 grams of oxygen gas. So we add enough energy, reach the transition state and all that. How much aluminum oxide are we going to get? But here's the situation now. You've got 4 moles of aluminum here in this reaction. 4 moles react. You've got 3 moles of diatomic oxygen that react. But you've got aluminum that has a molar mass. You've got oxygen that has a specific molar mass. So the issue is this. You know the basics. This gets enough energy, it breaks apart. So you've got some oxygen atoms running around. You've got some aluminum atoms running around, right? Do we have the perfect amount of aluminum atoms, right? And the perfect amount, or pretty much equal amount, to come up with this quantity of oxygen atoms, so everything that's in this beaker, right, winds up to be a final reacted product? We don't. One of these 2 things, aluminum atoms or a diatomic oxygen, we have less of. Because here's my thing. What if we break the bond and all these guys are trying to form new bonds, right, at that peak state? What if we're out of aluminum? Well, what happens to the aluminum? I'm sorry, what if we're out, did I missay that? No, I'm not editing it out. What happens if I'm out of oxygen? What if all the oxygen is done reacting, but I've got excess aluminum? Then it goes back in there. Oxygen would be the limiting reagent. The limiting reagent is important because you want to go with the smaller quantity, because that'll give you an idea of how much is actually produced right here. Or, what if I have a lot of oxygen, a little bit of aluminum? Well, I can make some Al2O3, but if I'm out of aluminum to form a new ionic bond with the oxygen, right, then what are these guys going to do? Stay as unstable oxygen atoms? No, they're going to go back as diatomic oxygen. So if I run out of aluminum first, right, then that's going to be the limiting reagent. So when you see a problem where you're given 2 masses, and you want to see how much of that is produced, you got to figure out which one's going to run out first, so you get the accurate amount of what you actually get in the beaker. So that's where you have to understand the limiting reagent. Reagent, reactant. Again, think about that. Whichever one you run out of limits the amount of final product. So that's the limiting reactant. Okay, so 2 mass stoichiometry problems in this case to start to determine limiting reactants. So first, and I have it written here because I really don't have time to look up molar mass, I have it all written here. So you're going to start with aluminum first. Okay? And we're going to see how much aluminum oxide is produced. So I'm going to write down my given. And we have easy numbers, easy to understand. 5 grams of aluminum. And now already, my classes, you already know how to do mass stoichiometry, so you should be familiar with the mole ratio. Okay? This is more geared toward limiting reagent in excess. So what goes down here? The molar mass. I'm going to round it for simplicity. You high school kids that are watching this, I don't do sig figs. Okay? You know that. The molar mass is going to be 27 grams of aluminum. We know that's equivalent to 1 mole of aluminum. Okay, now, we need to transition to the other side. In order to transition to the other side to get to aluminum oxide, we have to go real time with this equation. We see in this actual reaction, now we're going to customize this. In this actual reaction, we've got 4 moles of aluminum, and we've got 2 moles of Al2O3 aluminum oxide. Cancel, 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 cancel. Okay, now that's our mole ratio. You guys on honors can better know what that is. My guys, you better know what that is. My challenge guys. Okay. So now we've transitioned over to here. How do we continue this problem? It goes back to the basics of dimensional analysis. What unit do I want down here? Moles. 1 mole. What do we want up here? The molar mass, because I want to end up in grams. So the molar mass of aluminum oxide is about 102 grams of Al2O3. Cancel, cancel. So now what I'm going to get right now is, looking at this data, how much aluminum oxide would be produced in this situation? And the answer would be approximately 9.44 grams of Al2O3. Okay, that's not a final answer yet. That's going to tell me, in my beaker at the end I got 9.44 grams. Already now you need to know, now we got to see what happens when we react oxygen. All we're doing is seeing which one produces less of this, right? That's what you want to base everything off of. That will determine the limiting reagent, okay? So whatever I produce less of, you can tie it back to I had less of this. But you have 5 and 5. I know that. But there's more to meets the eye here, even though these are the same, right? Think about the molar mass of aluminum. Think about how many moles we have compared to the ratio. What's the molar mass of diatomic oxygen? How many moles do we have here? So again, it's not just what you have in the beaker, it's how it relates to the equation and the chemical reaction itself. Okay. So second part, so we did one mass stoichiometry problem. Let's do another one. So we did this, so that's good. I always like to put my givens here to kind of keep everything organized. Yeah, I know I'm the most unorganized person in terms of the classroom, but I'm really organized in doing calculations. So now I look at my next given, 5 grams of diatomic oxygen. Okay, what goes down here? Grams of diatomic oxygen. We know each oxygen is 16, so it's going to be about 32 grams of diatomic oxygen is the molar mass. Cancel like units. We know 1 mole is equivalent to that. Why do I want to go mole right here? Because that will allow us to set up the bridge, the mole ratio, to allow us to customize this calculation to this reaction. Okay? So let's cancel, cancel. Now I got moles of oxygen. Let's color code the mole ratio since that's really important. In this reaction, to customize this calculation to that, how many moles of diatomic oxygen do I have? 3. I'm going to put that in red. 3 moles of diatomic oxygen. That looks like 10. Okay? How many moles in this reaction we have with this specific reaction of aluminum oxide? 2 moles of aluminum oxide. Now sometimes you can stop right here and tell me just by moles which one's the limiting reagent. I want it done in mass. You know what? I want to give you worst case scenario. You could stop it right here and determine the limiting reagent right now in moles and that would be fine. But for my guys, challenge science, sorry, I want worst case scenario. I want you to go all the way to grams. Why? Because I want to try to do as much as possible now so you're ready for down the road. So anyway, now you honors kids, if they tell you to stop at moles, then stop at moles. I don't care. Same idea. Okay, over here. What unit goes down here? 1 mole. What do we want to solve for? Grams. What's the molar mass of aluminum oxide? 102 grams of aluminum oxide. So our final answer is going to be about 10.6 grams of aluminum oxide. So now my question is this. Which one is my limiting reagent? Which one do I have less of? Well, whichever one gives you less aluminum oxide, so it's going to be this. This gives me the limiting reagent. So ultimately, aluminum is my limiting reagent. I'm going to put up there an LR. Okay? This will be in excess, but wait a minute, let's go back to this. Remember we said, if we have enough energy, we break apart the diatomic oxygen. Break the bond. Add that energy. So for a little while, we got aluminum atoms, which are pretty active, running around with oxygen atoms. But here's the problem. In real time, we run out of aluminum, and there's excess leftover oxygen atoms. Okay? So now, that tells us aluminum is the limiting reagent, because that's why we got a smaller amount of aluminum oxide. So now the next part of this problem is, I want to determine how much excess reagent reactant we have right here. So now you're going to do a calculation that works with these two substances. So right here, this is like part A, okay? Now we're going to do part B, excess. Now watch this. So we start off with, look here, we start off with 5 grams of aluminum. We start with our limiting reagent. Start with the limiting reagent. Always start with the limiting reagent. Set the problem up just like before, okay? We know that aluminum has 27 grams. Its molar mass is 27 grams of aluminum per 1 mole. Okay? Now, cancel, cancel. Now, again, now we're going to customize it to this equation. We want to go from aluminum to oxygen, but we need to keep moles, so we're going to use our mole ratio because we're going to make this real time. Because in this reaction, it's 4 moles of aluminum per 3 moles of diatomic oxygen. That makes this calculation down here customized to the reaction up here. So now I want to do the mole ratio. I'm going to do that in red. How many moles of aluminum do we currently have? 4 moles of aluminum. How many moles in this case of oxygen? 3 moles of oxygen. Diatomic oxygen. You can stop right there, but I want it in grams. I want actual grams. Continue on with the problem. Cancel, cancel. What unit goes down here? Moles of O2. What goes up here? Grams of O2. I want to figure out how many grams we have right here. So I've got 1 mole, and my molar mass is going to be 32 grams. So overall, now here's what the answer is. Given 5 grams of aluminum in the beaker, that's my limiting reagent. What I'm going to get right here, the answer, I'm going to tell you the answer, is 4.4 grams of O2. So what is that? Is that how much excess I have? Or does that tell me, given this, only 4.4 grams of oxygen can react because I don't have that much aluminum? So let's go back for a second. Let's go back to what we said up here. We know aluminum, we have less of it, okay? So now I got 5 grams of diatomic oxygen in the beaker. So my question is this. We know this is the limiting reagent. So again, go back to bonds break, right? So I've got a bunch of aluminum atoms running around. I've got a bunch of diatomic oxygen broken apart running around. My limiting reagent is aluminum. Oh no, we're out of these guys, right? So some of this goes back to this. Is it 4.4 grams? No. 4.4 grams reacted. And once we had 4.4 grams of O2 reacting, it stopped. That was it. Okay? So the excess reagent is going to be this value, what reacted. So this is how much was reacted. Okay? What's the original in the beaker? 5. Subtracted. What's the excess still in the beaker? 0.6 grams. Okay? Alright. So that's with mass. I hope that helps. I hope that was described pretty well. I think you guys can see that pretty well again. You people at the high school, you got it good over there with your technology. This building, man. Hopefully you can see that okay. Alright. Got it? Alright, now I'm going to make a part 2 video.